In this video, we're going to start to take a look at section 10.1, Goodness of Fit Test. Chapter 10 is going to introduce for us a couple of new hypothesis tests that are going to have some different sounding hypotheses to the test that we've looked at in previous sections. Fortunately, the best part about Chapter 10 is that we're still doing hypothesis tests, so a lot of the things that we've learned in previous chapters will still apply. Let's take a look here at example 1 to get the sense of what exactly a Chapter 10 question is going to sound like. So here's what we got. Suppose a tax preparation company wants to determine the proportions of people who use different methods to prepare their taxes. So when tax season comes around, obviously people are going to finish their taxes in a variety of different ways. They may do it themselves, they may give it to somebody else to do for them, and so this is what the tax company is going to try to figure out. So a previous survey claims that the distribution shown below, that is, to test the previous survey's claim down here, we're going to go ahead and see if we believe these numbers. So the previous survey maybe shows that 25% of people use an accountant to finish their taxes. Maybe 20% of people do the taxes by hand. Maybe 35 use some computer software. Maybe 5 pass it off to a friend or a family member, and maybe 15 actually use this specific tax preparation service. Okay, so this is, of course, though, maybe some old information. Again, this says this is from a previous survey. So we might want to know, are these numbers, are all 5 of these percentages correct, or do any of them need to be adjusted? And so the way that we would maybe begin to test this is, again, to go collect a small sample of individuals. So to test the previous survey's claim, the company randomly selects 300 adults and asks them how they prepare their taxes. The results of the survey show 71 use accountants, 40 complete taxes by hand, 101 individuals use computer software, 35 people use friends or family, and 53 use a tax preparation service. So if I was to go down here, I could see that on part A, I'm just going to be asked to fill in here 2 different things. What it is that I observed, and specifically the frequency of number of people that I observed falling into each category. And then I'm going to write down what exactly I would have expected to happen if my percentages were true. Okay, so let's start with what we observed, because that's pretty easy. The problem just kind of directly tells us this. The problem says that there were 71 individuals who used accountants. There were 40 individuals who did their taxes by hand. 101 used computer software. 35 used friends or family. And 53 used tax preparation software, or a tax preparation service, excuse me. So if I added up all these numbers again, that should come out to the 300 adults. This is how they kind of broke down. But what we're interested in is trying to figure out, well, how many adults would I have expected to fall into each one of those categories? So if there were 300 adults total, and 25% of people are supposed to be using an accountant, then how would I figure out this value over here? Well, if I was to just simply do 300 people and then multiply that by 25%, I could see that very, very quickly I'm going to end up with 75 individuals. I would expect 25% of the 300 to fall into this category. So I can see that I would have expected 75 individuals to be in this category if 25% of people is the right percentage. Now we only got 71, so there's a difference there. And what we want to know is that difference just, well, it happens by random chance, you didn't ask everybody yet? Or is that an indication that maybe this percentage is wrong? Okay, well, let's continue down the list. Notice to get all of these other values, we're going to do, again, very simple calculations. Here we're going to do 300 times 20%. The next box we would do 300 times 35%. Notice again, we're just taking these percentages and multiplying them by the 300. If I kind of continue that on down, I think I'll end up with the following numbers in my box, and you can go ahead and confirm that the numbers that I'm writing here are indeed accurate. So these are the values that I would have expected to get. And again, I can see that some categories seem kind of close. Maybe like this by hand category, there's a difference of like 20 people. That's pretty far off maybe. Friends and family, there's a difference of 20 people. Some of these are only over under by 4 to 10, somewhere in there. And so I might ask a question like part B. We can see that what we observed in the sample does not completely reflect what we would have expected to see if these percentages were all correct. So what are the two hypotheses that can help explain the results of the sample? Well, I'm going to go ahead and start by writing out an H0. Here's my H0. I could say the percentages from the previous survey, these percentages are correct, and we just obtained an unlucky sample by random chance. Right? I mean, that's one possibility. There's nothing wrong with the given percentages. We got some slightly different numbers, but that happens just by random chance when you don't ask everybody. Of course, that's only one possible explanation, and another explanation could be that the percentages from the previous survey are not all correct. Maybe some of them are correct, but maybe not all of them are correct. And the sample is evidence of this. Right? This is kind of how we're thinking about this dilemma or this question that's at hand. Are these percentages that are given correct? Well, they might be, or maybe one or more of them are wrong. And we could probably even guess which ones we're most suspicious of at the moment. The bigger the gap that occurs between what we observed and expected, the more suspicious we're going to be. So these would be the hypotheses that we want to try to test with, or test. And in order to do that, we're going to have to create what we refer to as a goodness of fit test. We want to figure out how good each of these percentages fit the observed frequencies, or vice versa, how well the observed frequencies fit the given percentages. Okay. In order to do this, though, we're going to have to create something entirely brand new for this section. We're going to be creating a brand new type of distribution. So we'll see here that we have a new Greek letter popping up. It looks like an X, but it's actually a Greek letter of chi. You can see it here. Okay. So this guy here is a Greek letter chi. It's a chi-squared distribution. Okay, chi-squared distribution. Ultimately, this distribution has a lot of mathematical motivations behind its construction. I have, again, a big formula over here to indicate how exactly you would graph one of these distribution curves. It's just there to actually be scary. Ooh, a lot of scary information. Okay. For our purposes, though, we just need to know a couple of these basic facts about this new distribution and understand that it's something that we will be using when we do this goodness of fit test. So first off, the total area underneath our chi-squared distribution curve is still going to be 1, just like it has always been an area of 1 under every curve we've sketched with continuous distributions. A chi-squared distribution starts at 0 on the horizontal axis and extends indefinitely or infinitely far out to the right-hand side. If we were to go ahead and see if this curve ever touches the x-axis, it does not. It never touches that horizontal axis. It just gets really, really close. This curve is not symmetrical, unlike the normal distribution and the t-distribution. It is not symmetrical. And the chi-squared distribution is actually a bunch of different possible curves, kind of like how with a normal curve, we had lots of different ones that were based on means and standard deviations. But this set of curves is going to be based off of what we refer to as degrees of freedom. It's a really weird new value, but ultimately it's typically going to look like n, the sample size, minus 1. And as you change that value, you're going to change from the curves with like these big peaks to curves with these smaller peaks. As these degrees of freedom increase, then we can see that the chi-square distribution is going to become more symmetrical looking. You can see over here I have a V kind of standing for those degrees of freedom, and you can definitely see as that V value gets higher, I get something that's a little more symmetrical or bell-shaped. Okay. Ultimately, the chi-square goodness of fit test that we're constructing in this section is designed to test whether a specified distribution, whether a given set of percentages fits what we would expect to happen. Okay. So we're going to be going ahead and trying to see how this plays out, and we'll look at the general overview of all the parts of this test in the next video.